our publisher actually has been releasing some new videos that set up an introduction to some of these chapters, which actually they're doing a very good job, but they're not available or they're not really as good for all the chapters. But I thought that it was particularly good in this case, so I wanted to show you an intro just as another example to what a street routing problem is. And there's a link below, and there's also a link in the lecture slides if you want to watch the rest. But this video actually gets into the details of actually solving it, which is what we're going to be developing in the next few sections. So I'll just go ahead and play it and talk a little bit about it.
In this video, we will discuss sweeping. Not the kind done with a broom, but rather the kind done when doing a complete survey of a place or area. Imagine you're a professional photographer, and you've been hired by a real estate developer to photograph all the homes in a new subdivision. Your first assignment is to sweep this 3-block by 3-block subdivision and take pictures of the exteriors of all the homes within it. Let's assume, for starters, that you will park your car somewhere in the subdivision and sweep the subdivision on foot. When you're done, you'll get back in your car. This is what we will call a closed sweep. Here's a good parking spot. And off you go. All done. Now, unless a secondary goal was to burn a lot of calories, this was a somewhat inefficient sweep. There was too much deadheading. This is the term we will use for doubling up on already visited blocks just to get to new blocks that you haven't yet visited. This is a much better closed sweep. There's only 4 deadhead blocks. Could we do even better? Could we find a sweep with just 2 deadhead blocks? Or better yet, a perfect sweep with 0 deadhead blocks? It turns out that the answer is no. This sweep is optimal, meaning that there is no way to improve on this result. It takes a minimum of 4 deadhead blocks to complete a closed sweep of this subdivision. Furthermore, in an optimal closed sweep, the deadhead blocks have to be these 4. The question is, how do we know this? And more generally, with more complicated street networks, how can we determine the characteristics of an optimal sweep? How many deadhead blocks will we have? Which ones? Surprisingly, the answers to these questions were discovered roughly 300 years ago by the brilliant Swiss mathematician Leonhard Euler. To be clear, Euler did not discuss subdivisions or even street networks, but rather established his ideas in the more abstract setting of graph theory. Before we go on with the theory, let's first revisit the idea of a deadhead block. What if we think of a deadhead block as a new imaginary block being added to the street? If we do that, every pass becomes a new fresh pass. And this sweep becomes this sweep. A sweep we can visualize as passing once and only once through each block of the reimagined subdivision. We will call this type of sweep an Euler sweep.